Hi, I'm Reed Pritchard, and I'm going to be talking about a parametric study we performed on a mechanism shark skin possesses that is able to prevent flow reversal. First off, a little bit of background. What is flow separation and why does it matter? Flow separation is a generally undesirable phenomenon where fluid flow does not adhere to a surface. This breaking away of fluid from the surface causes control to be lost. So you can see over here in this diagram of an airfoil, you would think that flow would be going downward and to the right because of the way the airfoil is shaped. However, the flow kind of hits that leading edge and just skips across and ends up going upward and to the right. This isn't good. The airfoil should be producing lift by moving the air downward, but instead it's producing negative lift by moving that air upward. In airplanes, this phenomenon is known as stalling, and it's a big deal. Stalls caused about 20% of all fatal crashes that occurred from 2000 to 2014. In addition to this big impact on human life, flow separation also limits airfoil design. Really, in general, throughout fluids engineering, you see lots of compromises where performance is sacrificed because compromises have to be made to avoid flow separation. Now, flow reversal is the precursor to separation, and I'll talk about that on the next slide. Sharks are apex predators. They're agile, they're fast, and a lot of this is from structures on their skin that are called denticles. Past research has been done on denticles, but most of it has focused on their ability to reduce drag. However, they have a second characteristic that has only recently been discovered, and that is that they're able to mitigate flow separation. Flow separation begins with reversal of flow in the boundary layer. So right before flow separates from a surface, it starts moving the wrong direction right up along a surface. This reversal lifts the denticles, causing them to interfere with the flow and re-energize it and cause it to reattach. So it kind of stops flow separation right before it actually starts. Insight into this mechanism is pretty lacking aside from a few experimental studies. First, some details about our study before we jump into the results. So the objective of this study was to look into the flow separation control mechanism of shark denticles by simplifying it as a couette flow. Now, this couette approximation is not entirely physically realistic. However, it allows us to do a very broad parametric study as a preliminary exploratory study on the phenomenon to kind of paint a broad picture of what's going on. We approximate high momentum turbulent streaks as a moving wall at the top of the domain. So this flow is occurring in the viscous sublayer. We performed this study using ANSYS Fluent in double precision, and you can see our two-dimensional geometry on the right, where there is a thin denticle with length L, and it's bristled at an angle theta. There's an adverse pressure gradient moving against the flow, and in all cases this was a 3 millipascal gradient over our domain. The upper wall is moving to the right with a velocity of u, which we vary over the course of our studies. And as mentioned, this flow is occurring in the viscous sublayer, so we are just using a laminar viscous model. There are a few characteristic numbers and metrics that are important to understand for interpretation of our results. First is the Reynolds number. You're probably familiar with the Reynolds number, but if you're not, it just represents the ratio of sort of the turbulent nature of a flow. So a higher Reynolds number is more turbulent. For this, we're using the channel Reynolds number, where our characteristic length is the height of our domain, so the distance between the two plates of the couette flow. We control the Reynolds number by varying fluid density and viscosity, which is one advantage of a computational study, as we can vary these parameters very easily. The next characteristic number is the Lang number. The Lang number represents the ratio of the pressure gradient in the streamwise direction. So for our case, that's 3 millipascals divided by the length of our domain, to the fluid momentum, where that fluid momentum is before bristling, because once we add the denticle in, it's going to affect that, so that u is just the upper plate velocity. We controlled the Lang number by varying the density of our flow. The next number is a novel number that we have proposed called the Strasser number. And the Strasser number is 6 divided by the product of the channel Reynolds number and the Lang number. The Strasser number indicates the directionality of the net mass flow. So with a Strasser number of 1, there's 0 net mass flow. Greater than 1 means the flow is to the right, and less than 1 means the flow is to the left. We varied the Strasser number by scaling the physical dimensions of our domain and by varying that upper wall velocity. We also considered the dimensionless wall distance, y+, and we are using a geometric parameter called the blockage ratio. And the blockage ratio is L cos theta divided by channel height. So that's just the vertical projection of the denticle, the height of the denticle divided by the channel height. So a blockage ratio of 1 would mean the entire channel is blocked, 1/2 means half of the height of the channel is blocked, and so on. Our first output that we are considering is the mass flow recovery. And this compares mass flow rate to the mass flow rate of a similar setup without the denticle present and to the mass flow of a couette flow using the analytical solution. The important thing about this is it represents the ability of the given geometry we're testing to return the flow to a non-reversed state. So a large mass flow recovery means that the denticle is making the flow move rightward, and a negative mass flow recovery would mean that the denticle is actually impeding the flow and decreasing the net mass flow. The next parameter we considered is the peak backflow velocity, which we just measured to be the minimum x velocity along the midline, where that midline originates at the base of the denticle. We normalized this parameter according to the upper wall velocity, and we present this just as an alternate metric to quantify backflow mitigation. So just a different way of looking at the same thing as mass flow recovery. As previously mentioned, the advantage of doing such a simplified study was that it allowed a very broad parametric study. We have done this according to 2 parametrizations, where in the first we considered 8 different angles, 4 different denticle lengths, and 19 combinations of those 4 characteristic numbers, which comes out to just over 600 permutations. Our second parameterization used 4 angles, 20 lengths, and we just used 1 set of characteristic numbers, which gives 80 more permutations for a total of nearly 700. The first thing that's important to look at when considering a computational study is validation and also grid independence. This couette simplification allows comparison to an analytical solution. So that's another benefit, is we can go to a textbook and find the equation for velocity profile of a couette flow with an adverse pressure gradient, which is what we did. And you can see in that plot on the right 3 different cases, where those cases are combinations of characteristic numbers, which means different velocities, different domain sizes, and so on, without a denticle, of course. You can see that in all 3 of those cases, our computational results agree very nicely with the analytical solution. We also halved our mesh length scale to see the effects of that, and not only changed our mass flow recovery by about 1%, which we considered to be acceptable. Now let's take a look at some of the results, beginning with that first output of the mass flow recovery. One thing that we were very surprised to see is that the Reynolds number, the Lang number, and the Y+ had no discernible effect on the mass flow recovery over 12 tested cases, different permutations of different values of those. In all cases, any value we plotted of the mass flow recovery with respect to any other variables, they were all coincident. There was no difference. None of them had any discernible effect. The main driving factor was the Strasser number, which influences the relationship in terms of the slope and the curvature between the blockage ratio and the mass flow recovery. You can see in this plot, blue indicates a positive mass flow recovery, which is good. Red indicates negative mass flow recovery, which is bad. So where it's blue, the denticle is helping. Where it's red, the denticle is hurting. You can see in these first tested cases of 0.25 all the way up to 1.59 Strasser number, in all cases the denticle is helping and a larger blockage is better. So as you go vertically on the plot to a higher blockage ratio, there's more mass flow recovery. However, something interesting starts to happen right around a Strasser number of 2, where you can see the next highest Strasser number of 2.52, there are mixed results. With a moderate blockage ratio, there's a slight improvement to mass flow recovery, but then as the blockage gets larger, the denticle hurts mass flow recovery. You can see in the next largest Strasser numbers that the trend has completely flipped, where no denticle is best case, and as a denticle gets larger, as blockage ratio increases, mass flow recovery decreases. This makes sense because if you think about it, a large Strasser number represents a flow that's already moving in the positive direction. So if the flow is moving to the right and you put some sort of blockage in there, it logically follows that you're going to be decreasing mass flow rate in the rightward direction. Next, let's examine the peak backflow velocity, which again we normalized according to the top wall velocity. Again, we found that Reynolds number, Lang number, and Y plus did not influence results at all. It was the same deal where variation in that had no effect on results. Blockage tends to reduce backflow velocity. You can see in the lower numbers of Strasser number, it's less noticeable compared to the differences in backflow velocity as Strasser number changes, but you can see a slight darkening as you go vertically along a certain Strasser number. But with a large Strasser number, it's a lot less noticeable. So going up to Strasser number of 4 or Strasser number of 6, there are actually cases where even without the denticle, flow was 100% in the rightward direction. There was no backflow. So the denticle can't help things there because you can't have less than 0 backflow. Now let's take a look at the results of our second parameterization, where we held Strasser number at 1 and considered solely the geometric effects. We'd previously determined that blockage ratio has the primary effect on mass flow recovery, but here we decided to investigate the independent results of angle. You can see the plot in the upper right shows blockage ratio, denticle angle, and mass flow recovery. And up to a point, blockage ratio does increase mass flow recovery as we found. However, we saw there to be an optimum, where once you go larger than that, mass flow recovery starts to decrease. We also found that smaller angles are more efficient at improving mass flow recovery for a certain blockage ratio. Now, you can't think of this like a fixed length denticle pivoting to different angles, because with a given blockage ratio, a smaller angle means a longer denticle, because that blockage ratio is itself a derived parameter based on angle and length. So we found the optimum blockage ratio is right around 0.7. It depends on angle a little bit, and this result also needs to be interpreted with caution. It's certainly a universal conclusion that can be applied to couette flows with a blockage and an adverse pressure gradient. However, the physical realism of our approximation of turbulent streaks as walls begins to break down as the blockage approaches those. Because if the blockage is a long way from the streaks are likely unaffected by the blockage, but if the blockage gets up near the streak, that becomes less realistic. The backflow velocity plot is a little less cut and dried than the mass flow recovery plot was. Whereas we found the monotonic result with mass flow recovery that smaller angles are more efficient, here we found that the best angle depends on the blockage ratio. So for small blockage ratios, the shallow angle of 15 degrees found the lowest backflow velocity, whereas the 30-degree angle was optimum for a slightly larger range, the 45-degree denticle was optimal for a moderate range, and then the largest blockage ratios were had the lowest backflow velocity at that 85-degree denticle. In review, we found in this study that a small blockage in the viscous sublayer can significantly impede reversing flow. We found that blockage ratio is the primary predictor of that mass flow recovery, but we also found that for a given blockage ratio, lower angles are more efficient. An interesting conclusion was that Reynolds number, Lang number, and Y plus have no effect on any of the metrics we measured. And we also found that in this situation of a laminar couette flow with a Strasser number of 1, that a blockage ratio of around 0.7 is the optimum. We see many paths forward, but a few key future efforts we are hoping to conduct is first off, repeating the study with a wider range of geometries, such as that parameterization of 80, tested over all values of Strasser numbers. So here we considered a wide range of fluid properties with a narrow range of geometries, and then a wide range of geometries with just one Strasser number. But we'd like to get a little bit more granular data by combining those two and examining all three of those parameters independently. We also need to investigate our viscous sublayer assumption. It's very hard to get information on the boundary layer of an actual shark swimming in the ocean, so we need to perform a little bit more investigation to figure out if this approximation of the flow in the viscous sublayer with the turbulent streaks as a Couette flow, we need to determine if that's realistic. Whatever the case, these results present very interesting universal conclusions on a Couette flow with a range of Strasser numbers. Lastly, we are looking to perform a numerical counterpart to an existing experimental study to open the door to more advanced results if we are able to validate a more complicated flow. Thank you.